Yeah, so good morning. Now we are starting with a session for this morning, and good evening to guys in Africa. So we are continuing again with air conditioning or cooling, like they want to call it. There are two parameters in cooling, right? I'm sure most guys who are doing cooling understand this. The two parameters are temperature and humidity. Those are the two things that we always look at, right? Temperature and humidity. Those are I can say everything else is based around these two parameters that we need to look at, right? And today I'm going to show you the graph. They call the psychrometric, but I'm going to do it in stages. So I'm going to split it just to there's four main things that we need to know on that graph, and those are the things that I'm going to mention only because I know those are the things that will apply to you. And once you know them on the graph, you don't really need to know them on the graph, but once you know how to explain them, of which the graph explains them better, because nowadays we have the meters that are capable of measuring all these parameters, these four parameters, right? So that's why they don't really care about them anymore. But I find it very easy to understand this when you have a graph. When you understand the graph, that's when you can understand also the these parameters, which are temperature and humidity. So I'm going to firstly explain how these things affect data center. So one, high temperature is obvious. Equipment is going to get too hot and explode, right? That's easy, that one. Low temperature is going to promote freezing, right? So freezing means there's now water present, a lot of moisture present. That means components will start again to explode, right? Because you have unwanted channels, because water is a conductor, right? We know very well water is a conductor. So things are going to start to blow up again, right? That's easy. Then humidity. Humidity, as we say, high humidity means more moisture in the water, in the air, right? So if there's a lot of moisture in the air, it's easy because we have components that are operating at a lower temperature, and we have components that are operating at a higher temperature as well. So those ones that are operating at a lower temperature will start to condense. You understand that later when we explain this graph. And when condensation happens, that means water, remember the condenser from yesterday, water will start to accumulate on the components and stuff will start blowing up again. The low humidity, again, it's our enemy. Why? Because the air becomes too dry when you don't have enough humidity in the air. When the air is too dry, that's when we see it, like last year now in Zimbabwe. Remember, we had very low humidity and people started having headaches and stuff. Yeah, but it's not really for the people here. We're talking of data centers. So we have what we call electrostatic, right? It's easy. Electrostatic is that one when there are jerseys or clothes that you wear that will start to spark. That will happen around our data center. So we have static electricity. The level will be very high if we don't have enough moisture in the air, right? So we need to be right at the point where there is a balance. That's the reason why they came up with this guy called the psychrometric chart. Now you understand. I'm going to explain as well, going back to yesterday, which are the AHU, which is the air handling unit. And so the air handling unit will be just checking those things when you put your settings on the air handling unit, and the BMS is just going to monitor to see if the BMS doesn't control, it just monitors. It just shows you, hey, and you give it settings to say, give me an alarm if this starting happening. Give me an alarm if there's no power to my system. Give me an alarm if it's high temperature. See? That's all you do. So the BMS doesn't control, it just monitors. It's the monitoring system. So I just want to put it out there. So the air handling unit will take fresh air from outside. They always take fresh air from outside. That's why they replace the normal air conditioning systems, which are the DX, direct expansion, the one we discussed yesterday, this one behind me. Because why? This thing just circulates the air that is inside the building, right? It doesn't take air from outside unless the new ones that can provide for that. But all these ones, if you look at them, most of them, they don't take air from outside. They just circulate the air that you are in. So you are either cold or warm with the air that is circulating in your house. It doesn't take really the air from outside for most designs. Newer designs, they are doing that, right? So, so you end up having a lot of carbon dioxide in your house. That's why they get to come up with air handling units, which are for bigger scale. This one for your house, it's all right because you don't really take a lot of air. But imagine you have 100 people in a room. This won't work because the amount of oxygen that you're gonna need is a lot, and the amount of oxygen that's going of carbon dioxide that's gonna be produced by 100 people, it's gonna be intense in machines. You see, so that's why they come up with the air handling unit, which is the intake and the discharge, or they call it the supply, which is supply of fresh air. But that fresh air, when it's coming in, imagine we are in Zimbabwe, we are in winter. Our winter is not that cold, but it's like 11 degrees. So, or sometimes, yeah, 5 degrees, for example, the air is coming in, but now people can't handle that air. So what we need to do, we warm it up. What do we use to warm it up? We use boilers or electric heaters via the air handling unit, and give it a bit, check it for humidity. If the humidity is right, if it's too low, we add. If it's too low, we add a bit of water. By what? How do you do that? We use spray. There's sprays or there's steam humidifiers. Remember this spray. It says spray. No more spray or steam humidifiers. If it's too high, we dehumidify it. We don't heat it up. We dehumidify. Dehumidify is by the use of dehumidifiers, right? They just promote condensation. So they just initiate condensation so that some of the water will condense, thereby eliminating it from the air. Those are the questions. I'm giving you the pointers of the questions that get asked a lot, because they know people say, nah, if you have high humidity, you want to lower humidity, just heat up the air, but that's not true. Yeah. So from the temperature heat up or high temperature, they lower it. How do they lower it? By use of chillers, right? The chillers, using the chiller water. That's how they reduce the temperature, which is the one that you're gonna be asked a lot. So heating up as well, they may use some of the air that is coming out of the building. Remember, people or machines produce a lot of heat. So that heat, they may use it to warm up the air. That's how they save on heating system. You remember, heaters, they take a lot of power, remember? So they use that air, which is from the discharge, because they will be having from this end of the room, they will be having fresh air coming in with the air handler. Then on that side of the room, they have the discharge. So they use that discharge line, which is of right temperature, to warm up a bit, or they use different processes. But if you can watch that engineering mindset channel that I've talked about, they explain this topic, specifically this topic, very well, right? And retain some of the carbon dioxide water, but they have to check it if the carbon dioxide at the right level or what percentage they must bring in. Or also it determined by whatever air is coming in, how much oxygen content does it have. If the oxygen content is too low, then they can't bring in the used air, but they're just trying to save on heating. But air handling units do that on their own, right? So we are now going to explain the psychrometric chart. So the psychrometric chart is easy. Remember, it's always two main things: temperature and humidity, right? So when they are explaining it, so how do we manage our temperature, right? So we all did, I'm sure we all did maths at O level, A level, different stages, some of to university and stuff. And so on the horizontal or the x-axis, right? On the horizontal or the x-axis, the bottom one, this is normal temperature that we measure in our room, right? The normal temperature. But I want to make it a point that these guys use the fourth quadrant, right? So remember the quadrants around the when you're plotting graphs. So they use the fourth quadrant. I don't know why, but that's what they thought is best to use. So it's the fourth quadrant. It's not on the normal first quadrant that we normally draw our graphs. So it's on the fourth quadrant. But don't worry about that. I'm going to make it as simple as I can. So the horizontal axis, right? Temperature is increasing from 0, 20, 40, 80, 100, going like this, etc., right? 20, 40, 80, 100. Temperature is increasing. That one is normal thermometer using mercury, the old ones, or those ones that they put on your armpit if you go to the hospital. Those are that's a normal temperature reading, right? So that is easy. Number two, which is not difficult, you need to understand what they call the saturation line, right? So the saturation line is just a curve, and let's call it an infinity curve. Saturation line means this is the point where it's just like this. It's a curve, right? At this point, you cannot add any more water in the air no matter what you do, right? You cannot add any more water or any more moisture or any more grains. You're going to understand the grains story of water in the air no matter what you do, right? No matter you increase the temperature, no matter what you do. So there's nothing here on this side of the graph. So this is the 100% saturation on the air. If you try to add any more water, it will start to rain, right? That's when you receive rain. So you cannot add any more water on this side of the graph. This is the 100% saturation line. So what do they do to measure that? What do they do to measure that? They record what they call the word bulb temperature. So the word bulb temperature is just a fancy word, yeah, but it's nothing, right? Let's just say, for example, you take a sauce, you dip it in water, right? You start swinging, right? At first, it will be releasing a lot of water at a certain temperature. If you are inside your house, maybe it's a bit warm, you will reach a point where it doesn't want to release any more water, right? No matter how much you swing, right? So they stop there and they measure what is the temperature at that point, right? You understand? That's all it is. But they use what they call the sling psychrometer. They just sling it. That's what they do. And they plot the graph. So the temperature will be going on this saturation line. That's where they are plotting their graph. Then 20, 30, 40, 50, whatever, until 100. So they'll be plotting on this saturation line. That's where they plot the wet bulb temperature, right? It's a fancy word, but it's just temperature measured with a wet cloth. That's all you need to really know about it, right? So we have now three things. We have the saturation line. Just remember the saturation line. Remember the wet bulb temperature is always plotted on the saturation line. And we have the temperature, right? Going this side. We're only talking about temperature for now. But in the bit of saturation line was a bit of humidity. So don't worry about it for now. Now, with temperature, we are basically done. These are the two temperature measurements they give you. So the wet bulb temperature and the normal temperature, right? That they use with the thermometer. So this one, they use thermometer on the normal temperature, like normal. And the other one, they use the sling psychrometer for the wet bulb. Yeah. Not my favorite topic, but we need to know this because this is the stuff that they get to ask you. Yeah. So now the next parameter, which is the humidity. So humidity, we say it a lot, right? But there is two terms to define humidity. One, which is called the specific humidity. You understand? Specific humidity, which they draw on the y-axis, but only the top part of the y-axis, right? So start from whatever amount, 10, I'm just going to put easy number, 30, 40, 50, going up, right? So these ones are not, these are drops or grains of water. If you have a microscope, what do you call it? A magnifying glass or a microscope, right? They literally count how many grains of water are in 1 kg of air of a certain room. So you go to a corner of a room, right? You take 1 kg of air. I don't know how possible is that. And then they count how many grains of water are in there. You understand? So it's nothing, really nothing. 1 kg of water. So specific humidity is the amount, is the grains of water in 1 kg of air. I don't know how they did that, but they have to count how many grains are in there. So they take 1 kg of air, they count the number of grains in there. So they start from whatever, 10, 20. But I know the numbers are not exactly like I'm saying, but that's how they calculate the specific humidity. So they need to know exactly how much grains are in there. You understand? So it's nothing fancy. Nothing fancy. Just specific humidity is just the amount of grains per kg of air. Right? So 10 grains, 20 grains, 30 grains, 40 grains going up, right? That's how they do it. Now, we spoke of the saturation line, right? And now what they do is the most important humidity that we talk about is normally measured in percentage, right? So it's percentage to what? It's percentage to the saturation line, right? At what? At a specific temperature. So in relation to the temperature in that room. So only they need is two parameters, either the specific humidity and the temperature, the dry temperature. Then they will construct to see what is the relative humidity at that point and what is the wet bulb temperature at that point and what is the dew point. So that question will be asked a lot, what is the dew point, right? The dew point. That's the point where condensation starts to take place. You understand? So if you put anything that is lower temperature than that temperature at that specific humidity, stuff will start to condensate. The air will start to condensate. So perfect example would be water glass. You pour in very cold water in a water glass in a hot day, you put it out on the table, it starts to have water on the outside, right? That's condensation happening. Why? Because you put a glass of water which is lower temperature than the surrounding, than in the room, right? So condensation starts taking place. So condensation is our enemy. That's why we need to know what is the dew point. That's very, I'm sure it's a lot of words, but that's very easy once you get to understand. So what they do is, for example, we have two parameters only. They just give us, we have temperature of 80 degrees, right? Going up, remember our temperature is from bottom, this normal temperature, it's 80 degrees, and probably we have the humidity of, we have the specific humidity of 20 grains. So when they meet, all they do is they draw a graph. This curve graph. So they were using all these graphs that are curves like this. These are called the relative humidity graphs. You don't really need to know all of that, but relative humidity is measured at a specific temperature, right? Is the amount of water in the air at a specific temperature. That is relative humidity. They measure it in relation to the temperature, right? So relative humidity is always a percentage. So the saturation one is 100%, always remember. Then we have more graphs in there, which is 80%. So they will reduce going the other side. That's all you need to know. They reduce going the other side up until they go, a lot of them. Those are the ones that are most confusing for most people, but don't worry about them, right? Those are the ones that are there. So all they do, they just help you plot. Not that they're going to ask you most about this, but I just want you guys to understand it, because you will, if you can understand it, that's how you know the dew point, how you remember dew point, how you remember relative humidity, how you remember specific humidity, how you remember wet bulb temperature, all of that stuff. So you only need two parameters to be able to get the rest of them, right? So now, so where they meet, if we continue, so where they meet, right? If we just continue from The specific humidity line is a horizontal line until we meet our saturation line. That's how we get the dew point. Remember, we spoke of the dew point. That's how we get the dew point, right? And the dew point is important to us. Why? Because we need to know at what temperature does condensation start taking place, right? So the dew point for here now, it goes straight. Remember that we said it's measured, the dew point is measured and on the wet bulb temperature side, right? So we can go to the wet bulb temperature and see, here, this is the dew point at this wet bulb temperature. So probably here with my ugly numbers, it's gonna be around 25. Then we go down horizontally from that saturation line horizontally. Then we'll see that it's according to my graph, it's around 30. We must not go lower than that temperature as well on the horizontal line temperature, because condensation will start taking place. You understand? So don't worry about most of the things, just need to know the dew point. What is the dew point? How they know the dew point, right? But I can say that's all about that's all you need to really know about the psychrometric chart. Unless you are into refrigeration, that's when you need to know deeper stuff. But basically, this is how you know. You need to know dew point, to find dew point, saturation line, what is relative humidity. So relative humidity is always a percentage, right? You measure it's in relation to the temperature, to a specific temperature, right? That's the relative humidity. So what's the relative humidity at 80 degrees temperature? You just go to your graph, you go up, and there we have to give you two parameters. They can't just give you one. Either they give you the wet bulb temperature and the normal temperature for you to be able to find out what is the specific humidity and the relative humidity. You understand? Those are the only things that you need to know. You don't need to know the math behind it or very other bigger terms behind it, because remember, you are in the maintenance team mainly, right? But if you are interested in this topic, just go and read about it more or watch a few videos. I can recommend TechTube. TechTube is, the guy explains quite well the simpler things, and there's some slides there to show you. So it's called TechTube, TEC, Tube. Yeah, they are good. They are good. I think that's the simplest you can ever get on that one, right? So we see that we need our humidity and our temperature. Those are our two main things that that is our enemy, right? So with these two things as well, which are our enemies and our friends as well, with these two things, that's how they got to come up with what they call free cooling. So for free cooling, they just look at these two parameters and realize, okay, but this is all now being done by BMS. So it's going to see, okay, at this point of the day, like, for example, places like Harare, right? We know very well that in Harare, maybe at night, probably in a winter day, it goes down to 5 degrees Celsius. So that's the only time our air handling units go to work, right? To try and increase the temperature in the air, right? That is coming in to our data center. And on a very hot day when it reaches 35 degrees, that's when only our air conditioning system, which is our chillers, start to operate. to try and check out the heat from the equipment, right? So this is how they made it possible. It's actually cheaper in Africa to run a data center than it is here or in most places. New Zealand is quite good also on the weather. Yeah, if you look at the north side of New Zealand, North Island is quite good because it never reaches freezing and it never gets too hot, more than 25 degrees. So you can literally run here on free. But remember, we don't just look at temperature, we also have to look at the humidity. That's the enemy here as well. Because here in New Zealand is quite damp, right? It carries a lot of moisture. So you have to look at how do I have to remove the water. So that means your dehumidifier needs to get in place. So that means that's how you're going to lose. Because remember, all the money that we lose in heating and cooling cannot be recovered. Because remember, we're just playing with air. That's all we're doing, right? And from then, we are, so if it's like Zimbabwe, for example, there's not a lot of dampness in the air, so they can operate at a free. So what will happen is your air conditioning, your handling unit will be taking the air as it is using just the fan to take the air in, right? Because most of the time it's operating at it's operating on free cooling mode. So it will be saying on the BMS system, it will be writing that now operating on free cooling mode, right? If you reach a certain time of the day, say from around 10 a.m. to around maybe probably from around 6, 7 when the sun comes up to around 11 a.m. it will be running on free cooling, and as soon as the sun goes down up until probably midnight, it will be also running on free cooling because the parameters are being met. Which parameters are we talking about? The humidity and the temperature. So high humidity, we have to use dehumidifier. Always remember that. You don't heat up the air. Like this graph. You don't heat up the air to reduce humidity. Even though from these plots, we can see that as we are increasing temperature, right? Temperature, it only increases the capacity of the air to carry more heat, you see. So we are only increasing the capacity of the air, but no heat up. Whenever we heat up the air, right, it can just take more moisture. It's not that we are reducing moisture from the air, but it just becomes capable of taking more moisture before condensation takes place, because we are running away from the saturation line. The saturation line, that's when we have 100% humidity in the air, right? And here, there's nothing here because we cannot add any more air, whatever, any more water. Once we add any more water, condensation starts taking place and it starts raining, right? Starts dripping. And dew point is always the temperature that we need to note. Why? Because we cannot put anything else that is lower temperature in that same room. That's when at that specific temperature, condensation will start to take place, right? And those are the main things about the air conditioning. So you see why this applies to our air handling unit and applies to our free cooling. So now I guess we have time to explain a bit about evaporative cooling. So evaporative cooling made possible for new data centers now to operate in dry climates. You understand? So all they do is, remember, it's hot. If you go to the Arabic countries, for example, Qatar or Saudi Arabia, it's very, very hot. So it's very, very hot. That means the heat is for free. You understand? So evaporation, like it says, take, for example, a pot, right? A pot, you put it, you boil it. You boil it, you put your hand a few, let's say, 10 seconds, 20 seconds, 30 seconds, 40 seconds, 50 seconds, 60 seconds, 70 seconds, 80 seconds, 90 seconds, 100 seconds, 200 seconds, 300 seconds, 400 seconds, 500 seconds, 600 seconds, 700 seconds, 800 seconds, 900 seconds, 1000 seconds, 2000 seconds, 3000 seconds, 4000 seconds, 5000 seconds, 6000 seconds, 7000 seconds, 8000 seconds, 9000 seconds, 100 seconds, 200 seconds, 300 seconds, 400 seconds, 500 seconds, 600 seconds, 700 seconds, 800 seconds, 900 seconds, 1000 seconds, 2000 seconds, 3000 seconds, 4000 seconds, 5000 seconds, 6000 seconds, 7000 seconds, 8000 seconds, 9000 seconds, 100 seconds, 200 seconds, 300 seconds,
meters or less than 1 meter away from the pot, boiling pot, you feel that as soon as your the steam, right, reaches your hand, you, even no matter how hot the water is, you start getting a cooling effect, right? That's the technology they used. That's exactly what they used. That cooling effect is when the fan takes that cooling effect straight into your data center. That's evaporative cooling. That's basically it. That's basically it. It's fancy, but it made possible for anyone. So all they do is they get a spray, right? It's just a pump, small pump. They need a small pump to spray the water into the air that is coming into the data center, right? And a filter to stop the moisture from going in. So adiabatic cooling and evaporative cooling are explained as one thing, but they are different. Was one takes the air directly inside, right? The same air that is spraying the water, it goes inside the building, which is now rich in moisture, remember, because it's going that same air. But for the adiabatic one, there's physical separation, right, of the two airs. The evaporative cooling will be happening on the one side, then the other air will be going there. But remember, we talk of fins, we talk of conduction. Yeah, that's the form of cooling that will be happening right there. But you can go and research more about it because it's actually a very hot topic. Just trying to simplify it for you to know the difference between adiabatic and evaporative is just one. Just that the evaporative one, it's the air, same air coming from outside with the air handling unit. It gets sprayed, right? Evaporation starts taking place, leaving a cooler effect onto the fins. Then that same air gets passed into the data center. So that's how easy it is. That's what they are using in there are way better and more complex examples about this. I know it's a lot of companies, I think Danfoss, if you follow Danfoss, they may explain to you how they're doing it, but most people don't really explain it well, but Danfoss, I guess they explain it better than everyone else because they actually have that small plant. I don't have much time now, but they have a small plant outside where it's just like a cooling tower where all this evaporative cooling happens, and